Much of the following explanation is adapted from Nobel Prize-winning physicist Richard Feynman's lecture on physics, a section called Electricity in the Atmosphere. For every meter you go up in the air, the voltage increases by around 100 volts, or we could say around 100 volts per yard. We can draw these voltage increases using what are called equipotential lines. Notice that the ground is negative and the sky is positive with respect to each other. According to Feynman, this extends upward to 50 kilometers, or 31 miles, where the air is very conductive. This is the case in fair weather. In stormy weather, like a thunderstorm, things are quite different, and I won't talk about that here. But if this voltage exists between your head and the ground, why don't you get a shock? The reason is that your body is a good enough electrical conductor that standing on the ground, you're basically a part of the ground. The equipotential lines would look like this. There's still effectively 0 volts between the top of your head and ground. Similar effects happen with trees, buildings, and so on. What about the electric current? A downward electrical current exists and consists of positive ions, molecules or clumps of matter that have a positive charge. These ions are moving slowly toward the ground. The current density from these ions is very small, around 10 microamps, or 10 picoamps, crossing each square meter or yard every second. So in any small area, there's not a lot of power. And that's the explanation about atmospheric electricity adapted from Feynman's lectures.
When we talk about the global electric circuit, we are describing how electricity naturally flows throughout Earth's atmosphere. It can be generated by the interaction of solar wind with Earth's magnetic field, down to the electricity that individual clouds produce. Clouds that produce lightning in a thunderstorm, for instance, feed electricity into the global circuit also. They're all a part of the same system. While we have known for a while that electricity exists in the atmosphere, scientists are just beginning to understand the relationships between the different events that affect it. Could the amount of electricity in the atmosphere change the way clouds and storms develop? Blue jets shoot out of electrified clouds with or without lightning. We use math to represent natural phenomena like how much energy Earth receives from the sun and the weather that emerges as a result, from tornado-producing storms on the Great Plains to hurricanes forming in the Atlantic. Trying to create a model for the global electric circuit presents incredible challenges. First of all, studying the global electric circuit requires experts across many areas. Scientists who specialize in the uppermost atmosphere, solar wind, electromagnetism, chemistry, the physics of lightning, cloud formation, volcanic weather, and more. Secondly, the model is trying to encompass events that are a part of the global electric circuit on vastly different time and spatial scales, from sprites that appear for a few milliseconds to the 11-year solar cycle, or enormous events like gamma-ray bursts down to small particles that influence cloud formation and cloud electrification. And there's even uncertainties about how clouds are charged and how atmospheric conductivity occurs and breaks down. So what is the global electric circuit? It's a system that encompasses all of the electrical generators, currents, and TLEs in Earth's atmosphere. Because of observations, satellites, ground-based networks, and observations of electrical phenomena between clouds and the ionosphere, we know a lot more about Earth's global electric circuit that transverses Earth's upper and lower atmosphere, but we still have a lot to discover about the system. Basic research will help us get the answers we seek.